All right, so the plan for today, just quickly again review attendance. I think we had everybody here but one person last time, and it looks like they are here, so we're good to go as far as registration and the roster and all that are concerned. And then we're going to start chapter 2. So starting with the tangent and velocity problems, and if time allows, moving into an introduction of the limit of a function. Um, Note that again, the WebAssign the chapter 1 material, the review material from WebAssign is available, and it's due this coming Sunday. So it looked like I think everybody has logged onto the WebAssign system and gotten in at least. So that's a good start. If you haven't, you can refer back to the previous video that's posted on YouTube, the information on Blackboard, all of that, and you can see how to go through the WebAssign process. And then the plan for this coming Monday, the next class, is to either start or at least finish up 2.2 and then move into and maybe complete 2.3 limit laws or properties of limits. So any questions on any of that so far? Any questions on anything last time, on WebAssign, anything like that? Okay, great. The quote of the day today is from the Greek philosopher Epictetus. This is a loose translation of a couple lines in his work that's often just called Discourses. And the quote, or the kind of loose translation, is conceit of knowledge gets in the way of learning. In other words, if we kind of think that we know everything, we're going to be unlikely to seek out new information or to accept new information when it comes along. And this kind of links to the ideas that I think are really relevant today in the information age, and we're surrounded by information. What information should be trusted, right? I mean, up until maybe 20 or 30 years ago, it was actually hard to get enough information for whatever problem you were looking to work on. But now we have so much information. The bigger problem, I think, is often sorting through that and finding the good information from the bad. A lot of people just say, oh, well, just rely on, expert analysis or information provided by experts. But all that this does is reframe the problem to, okay, then how do you define expert? What people should be trusted? Uh, what people should be given, be trusted with authority? And I don't think that's an easy question to answer either. People will give you answers, but then if you kind of drill down, it turns out that they usually are either saying, well, my experts are all of the people who are saying the things that I already agree with or that I like, or they're defining expert in some other way, and you can find counterexamples and say, well, do you really mean that, anybody with that degree is an expert? What about this person who says all kind of silly things but fits that mold? And it ends up becoming a no true Scotsman fallacy kind of situation. Like, oh, well, they're not really an expert even though they fit all of my criteria. I would know the difference between that person and a real expert. So it's not an easy question to answer, and I think it's very relevant for today. Okay, so if there are no questions, then we will move on to the material for today. All right, so moving into chapter 2 and section 2.1, the tangent and velocity problems. And we're going to start with the so-called tangent problem. And let's start with a motivating example. So we have a function f of x equals x cubed, and we want to know the slope at the point 2 comma 8. Now you might look at this and you might say, well, this is a funny thing to ask. When we talk about slope, we talk about slopes of straight lines, and this is not a straight line, this is a curve. Right? If we look at the graph of f of x equals x cubed, it looks more or less like this. And we have some point, say 2 comma 8 over here. Okay, so let's come off to the side and just remember what the idea of slope means. So just as an aside, if I have a straight line, and if I change my input x from, say, A to B. Then my output y changes from, say, C to D. So I go from A comma C to B comma D, or sometimes it's, X naught, Y naught, and X1, Y1, however we want to say it. And the idea is we have what's often referred to as a run, a horizontal distance change versus a rise, a vertical distance change. And we say that slope is rise over run, or it's the change in y over the change in x, the change in the vertical position over the change in the horizontal position. Or in this case, it would be what? D minus C over B minus A. Or it would be y1 minus y naught over x1 minus x naught. Now, the nice thing about a straight line like this is if I compute the slope using this AB and C and D on the X and Y axis, if I picked a different set of inputs, maybe if I use this instead, my run could be longer or shorter. I could translate it left or right. I could expand or contract. I'm going to get the same answer. So that's the nice thing about a straight line, is that the slope is a very nice and well-defined idea. And in fact, really the slope is kind of a function of just 2 points, right? Because 2 points determine a line, and that determines the slope for that line. So I can say, I can ask a question like, what's the slope of the line connecting 2 points? If I have 2 points under consideration, I can find the slope of the line connecting them. And there's really no ambiguity in that. It's not a question of where am I at on the line or how big is my delta x. We get the same answer no matter what 2 points we pick on that line. Now, one thing we would like to be able to do is we'd like to take this idea of slope, in a kind of a rough sense. This says like, how hard is it to walk uphill? If I move 1 foot horizontally, how many feet do I rise? The steeper the slope, the harder it's going to be to walk up that hill. And I might want to generalize that idea to apply to a function that's not just a straight line. I would like to take this idea of slope, of kind of steepness, and maybe apply it in a more general case that's not just a straight line. How can I do that? Well, let's step back for a minute and just kind of think for a little bit. Well, if I have my little person standing here, they're going to have a heck of a climb to go from x equals 2 to x equals 3, right? From height 8 to height 27, they're going to be like climbing up the side of a mountain. But if my person was instead standing here at, say, near x equals 0, things are much flatter. It's a much easier traversal. So one thing that I realize is, while for a straight line, it doesn't matter where I look on that straight line or how big of a run, so to speak, I take, I always get the same answer. But for a curve, I don't think I'm always going to get the same answer. I think that slope for a curve, instead of being a global property, like it is with a line where that same idea applies everywhere, it's going to be a local property. It's going to be near this point, this is the steepness. But if I go to a different point, I'm going to get a different steepness. Okay, so I want to generalize the idea of slope to curvy functions, but I don't want to just kind of throw everything out, right? I still want to use this basic idea. At some point, I have to do some calculations, and I want to use these ideas for my calculations. Now, one big idea that I'm going to use here, oh, as a side note, I forgot to mention, I posted these notes as a PDF and as a OneNote document in Blackboard just a little bit before class. So I forgot to mention that, but if you want to download those and work through it on OneNote or whatever, uh, I, I'll plan to have them posted a little earlier from this point on, but the first week's a little bit hectic. So, um, but the kind of outline of the notes is available on Blackboard. Okay, so we first have to talk about kind of a big idea in calculus. And my favorite professor, he was one of my grad school professors, Professor Layton. He's retired now, but he would always say the world is locally linear. So what did he mean by that? Well, let's take a look at, say, a curvy function like this. If I look at this function, and maybe I'm interested in the slope, so to speak, at this point, if I look at this function, I say, okay, it's curvy, it's not a straight line, it's not flat. However, if I take a small segment of this and kind of zoom in on that, I'll try to draw this fairly accurately, going from about there to about there. If I zoom in on this, it looks almost like a straight line. Right? Of course, none of my lines are straight. I'm not that good of an artist, but you can imagine if the red line was a straight line and the black line is the curve, the more I zoom in, the more the black curve looks like a straight line. And we're going to really leverage that idea. So we're going to leverage the idea that the world is locally linear, that when we zoom into a function or into a point on a function, if we're looking really, really close, it looks kind of like a straight line. So what I'm going to do is I'm going to consider this function blown up a little bit. And again, here I have a curvy function. If I was interested in finding the slope of a line, I would take one point, maybe the point of interest, say 2 comma 8. But I have an issue now. I have to pick a second point in order to be able to use my slope formula. Well, let's pick another point on the curve. We'll kind of make it arbitrary. So this is our point 2 comma 8. That's our point of interest. We'll pick another curve and we'll say that maybe, or another point on the curve, we'll say that maybe that point is, let me move Professor Layton out of the way a little bit here. We'll say that point is, say, h units away from 2. And typically we're thinking of h being a fairly small number. So I have this point sitting here at x coordinate 2 plus h. And then what's its y coordinate going to be? Well, that's just 2 plus h all cubed. Whatever the input is, I cube it. That's what my function says to do. But now I have 2 points. I can draw a line between them. And I can find the slope of that line. And now when I say the slope of the line, I really mean slope. I don't mean something kind of like slope. I mean the slope of this line. And in fact, this is an important idea. So we have a name for this. We call this the difference quotient. And a lot of times we might represent it as like dh, something like that, or something like d of h. This slope is going to depend on what I choose for h. If I choose h to be positive 0.5, I'm going to get a certain second point and a certain slope. If I choose h to be positive 0.1, I'm going to get a different second point, a different line, a different slope. If I choose to h to be negative 0.1, again, a different second point, a different line, a different slope. So let's just, I need a little bit more room here. So let's see then, what is d of h going to be? This difference quotient, this kind of, the slope of this line for an arbitrary h. Well, it's going to be the difference in the y's, the difference in the outputs, divided by the difference in the inputs. So that's my difference quotient. I suppose I could simplify this a little bit. The denominator just turns out to be h. The numerator, well, I need to cube something. I need to cube a binomial, so I use Pascal's triangle. I know my coefficients are going to be 1, 3, 3, 1. So I get 2 cubed, 1 times 2 cubed, plus 3 times 2 squared times h to the first, plus 3 times 2 times, whoops, times h squared, and then plus 1 times h cubed. That came from cubing things out, and then minus 8. If you're not familiar with Pascal's triangle and multiplying out binomials, you can Google that, but we see that these go away. And I actually see here that everything in the numerator now has a factor of h that can divide out with the one on the bottom. So 3 times 2 squared, that's 12, plus 6h plus h squared. If I left it here, I've missed a very important point. Very importantly, note that h can never be 0. That's a very important restriction here. If h was 0, my second point, so to speak, is just the same as my first point, and I don't have any line at all. I don't have any notion of what the slope is. So this is with h not equal to 0. Just because some stuff ended up canceling out, that doesn't get rid of that domain restriction. We cannot plug in h equals 0. So once I divide out the h, at a glance, it looks like I can plug in h equals 0, but I have to be very careful. And remember that domain restriction still exists. But what can I do? Well, one thing that I realize is, let me again draw a big version of this function with, say, a point of interest and maybe a second point. One thing I realize is that when I have my second point, h units off to the right, and I draw my line, this is what we call a secant line. In other words, it cuts the function. This coming from the Latin secare, meaning to cut. The secant line cuts the function, it cuts through it. If I start inching my second point, the non-point of interest, the other point, towards the point of interest, I still have secant lines, but they get closer and closer to, let me just undo these, they get closer and closer to this line that just touches at exactly 1 point. So this line, this green line, touches the curve at that 1 point. It doesn't cut it anymore. It just touches. We call this the tangent line. coming from the Latin tangere, same root as like tango, the tango dance, where the two people are like touching each other, meaning to touch. So we have a tangent line that touches, that's kind of in some sense the end result of picking a second point that gets closer and closer and closer and closer forever to that point of interest. It doesn't ever actually reach that point of interest, because if it did, that would be like plugging in h equals 0, and we'd have two of the same point, which does not determine a line. But in some way, this idea, not plugging in h equals 0, but picking h to be 0.1, then 0.1, then, or sorry, picking h to be 1, then 0.1, then 0.01, then 0.001. If I keep making h closer and closer to 0, but not equal to 0, my secant lines start looking more and more like this tangent line, this kind of abstraction in a sense. And then maybe I can guess, for instance, I can find the slope of each secant line, and maybe I can look at that pattern and guess what I think the slope of the tangent line should be based on that progression. If I end up in a situation where I plug in h equals 1 and I get a slope of 8 for that secant line, that kind of bad secant line, and then h equals 0.1 gives me like 4.1 as the slope, h equals 0.01 gives me like 4.01, and h equals 0.001 gives me 4.001 as the slope. Maybe I can guess, okay, I think as h keeps getting closer and closer to 0, but not equal to 0, the slope of the secant lines are going to keep getting closer, or are going to have slopes that keep getting closer and closer to 4. And maybe I would intuit then that I think the slope of the tangent line ought to be 4. Okay, so just to kind of recap, what do? We have a curvy function. We're trying to generalize this idea of slope. We have a point of interest because we need to say where we're at on the function for a curvy function, because this idea of slope is going to change whether we're here or there on a curvy function, even though it doesn't change for a straight line. So we say where we are, our point of interest. But then to get to manufacture a line and get something like a slope, we need a second point. We choose a distance h to go away from the x coordinate of interest. Yeah, is the slope of the tangent related to the gradient of the function? Yeah, so gradient is um, the word gradient has a lot of different meanings. There's a mathematical meaning of gradient that is essentially the same as the slope of the tangent line. It's essentially the same idea as the derivative, which is what we're working up to. Um, but there are also some ideas of gradient that are where that word is used more colloquially, like kind of general steepness or something like that. And it's definitely related to that. That kind of, that's our little guy up here who's kind of walking up the hill, and it's, getting steeper at some point. So yeah, good question. Is the term gradient, um, depending on its use, has either it essentially is the slope of the tangent line, or it's closely related to it. Yeah, so going back, we have our point of interest, we have our second point so that we can construct a line. And we see that as that second point gets closer and closer to the point of interest, our secant lines that cut the function start to look more and more like our tangent line that just touches it in one place. The nice thing about the tangent line is, this is all for nice functions like this one that work nicely. The nice thing about the tangent line is that it's actually unique. There's lots of secant lines. There's lots of lines that go through this point of interest and cut the function, but there's only one tangent line. If I tilt this a little bit, say counterclockwise, it's going to cut somewhere over here and it's no longer a tangent line. If I tilt it a little bit clockwise, it's going to cut over here and no longer be a tangent line. So this tangent line is unique as well. We have lots of secant lines, but one tangent line. Again, provided that our function is nice enough, which we'll see some examples throughout this chapter of not nice functions and the things that can go wrong, but kind of speaking in the situations where things work nicely here. So this is our big question. We have this idea of a tangent line now. How do we figure out the formula of the tangent line? Y equals mx plus b, or maybe more usefully, y minus y1 equals m times x minus x1. Either slope-intercept form, which maybe we're a little bit more used to, or point-slope form. Why would point-slope form be more useful here? Well, because I already have a point. I have the point of interest, x1, y1. So I already have the point for my tangent line. I want it to be tangent at the point of interest, of course. What do I need to find? Well, the main thing I need to find here is the slope of this tangent line. If I find the slope of the tangent line, I use that alongside the point of interest and the point slope form, and that gives me the full formula for that tangent line. And again, how do I find the slope of this tangent line? Well, I know the slopes of the secant lines for a given h. I can use my difference quotient up here to get that. That just came right off of plugging in an arbitrary h and going through the work here. And in this case, it's simplified out a little bit. Sometimes it doesn't simplify so nicely. But I can evaluate this difference quotient for different values of h, getting closer and closer to 0. I can get outputs from that that are slopes of the secant lines. As those secant lines get closer and closer to looking like a tangent line. And then maybe I can infer, looking at that pattern, what I think the slope of the tangent line ought to be. Okay, so we're going to do that in just a second here. Let me bring out my calculator and kind of switch my screen share around a little bit. My calculator is not being very cooperative at the moment. I went to open it and it just didn't want to open. I'm not sure why. Let me try to close it and reopen it. Let me try one quick thing because my calculator is not wanting to work at the moment. I have this emulator. It's called Wabbit Emu. Like I didn't name it, but it just worked like a few days ago. So let me try to get in here and try really quickly to check something. Okay. Well, we have first week challenges. So we'll pivot and we will use a different calculator. Okay. Just first week of class problems. All right, so we will use Desmos for our calculator. Let me rearrange my windows here a little bit. And we're interested in the function 12 plus 6h plus h squared, or 12 plus, we'll call it 6x, plus x squared to make Desmos happy. And this is our function of interest, and we're interested in what happens when x is near 0. So I think I can I do that? No, it doesn't like that. Let's see.
If you set it to any random variable, you can then assign the variable to 1.
Oh, okay, so like if I do A or something like that.
Yeah,
Ah,
with the
okay.
X slider. No, the button down there. Yeah.
Okay. All right. Cool. Thank you. Yeah, I was gonna bring up my TI-83 emulator, but that's not working at the moment. So, okay. So we are ready to go now. So remember that our goal is we want to find m, the slope of the tangent line. We're going to do that by looking at slopes of secant lines. And those of you who have some exposure to calculus already might know where this is ultimately headed, but um, we're kind of taking the slower approach. So you might see where this is going eventually, but we're not going to get all the way there for a couple of sections. So let me draw out a table of values for h and for d of h, where I'm starting with maybe some positive values for h like 1 and working my way towards h equals 0, but again, not picking h equals 0. So when h equals 1, what do we have for the answer here? Let's see. Maybe I need to zoom out a little bit. Should I do like y equals? Okay. Not the prettiest, but it works. Okay. So for a equals 1, we have, it looks like an output of 19. So for an input of 1, we have an output of 12 plus 6 plus 1 is 19. All right, that checks out. So the slope of the secant line going through 2 comma 8 and through 3 when h is 1 comma 27, that has a slope of 19. If a is 0.1, it looks like I have an output of 12.61. Okay, there we go. Now it says y equals. So when I have an input of 1 into my difference quotient, I have an output of 19. That's the slope of that secant line that still doesn't look very much like a tangent line. When h is 0.1, we have another secant line that looks a bit more like the tangent line, and it has slope 12.61. When h is 0.01, getting closer to 0, it looks like my output of the difference quotient is 12.0601. And we could probably guess what's going to happen as we add more zeros. We get closer and closer to 12. So we start seeing the pattern, and I say, I think as h gets closer and closer to 0 from above, I think my outputs are going to get closer and closer to 12. That will be my guess. Now, I suppose I could also approach this from the other side, so maybe I should check that side as well and make sure that I get a consistent answer. So I could also pick an h like -1, sampling my second point, say off to the left. There's nothing wrong with that. That's just as good of a set of secant lines to the left as the ones to the right. And what would be my difference quotient here? So if I picked a to be -1 instead, my output of my difference quotient is 7. So again, it's not a, sometimes OneNote tries to be too helpful. I get an output of 7 for an input of -1 when I'm using my 2 points as 2 comma 8 and 1 comma 1, that secant line has slope 7. Again, that's not a secant line that looks very much like my tangent line, but it's a starting point. If I go to negative 0.1, I get an output of 11.41. If I get a little closer to 0, negative 0.01, I get an output of 11.9401. And this is looking promising as well, right? It's looking like we're getting closer to 12. If I put another 0 in there, I get an output of 11.994001. And again, I kind of guess that as h approaches 0 from the left, in this case, from below, it intuitively feels like my difference quotient, my slope of the secant lines, is getting closer and closer to 12. Both of these two agree. That seems to be pretty good evidence. If from one side my slope is increasing to 12 and the other side it's decreasing to 12, this seems to be pretty good evidence that the slope of my tangent line maybe ought to be 12. Now, I haven't, proven this super carefully, and that's what the next several sections are going to be looking at. But I have, I think, given a pretty strong argument in favor of the slope of this tangent line being 12. So what is the slope, so to speak, at 2 comma 8? We might want to say it's something like 12. In other words, if you took one tiny step when you were standing here, the amount of kind of effort it would take, or when you're standing here, the amount of effort that it would take to go that kind of tiny step forward would feel a lot like the same effort climbing a straight line hill, a flat hill like that, that has slope 12. The kind of effort would be about the same. But just for that one little step, right? If I took 10 steps forward, well, then because my function is a curve, that effective slope is going to feel different if I go off to the right or off to the left, right? It's going to feel a lot easier over here and a lot harder further up. So we've uncovered a few different important ideas. One is that on a curvy function, we can generalize this idea of slope from linear functions, but we have to be careful because in a curvy function, this is a local property. It only is effective at a single point. That idea of slope is going to change from point to point on the function, unlike a linear function where that idea of slope is consistent across the whole function. And we get there by taking our point of interest, using a second arbitrary point to construct a secant line, looking at the slope of that secant line, and then moving that second point closer and closer to the first point to get secant lines to look more and more like a tangent line. And that's really the thing we're interested in. We're saying that kind of the instantaneous slope, in a sense, at this point on the curvy function, we're essentially equating that to the slope of the tangent line, to the slope of the line that touches that point exactly at one place and does not cut the function. At least does not cut the function locally, right? Maybe the function comes down over here and it cuts it over here, but it doesn't cut it near the point of interest. So we've answered our question. We've said the slope is 12, this generalization of the slope. The slope of the tangent line is 12. And again, we can find the equation of the tangent line if we wanted. Can do y minus, well, y1 was 8. That was our output for our point of interest, equals 12 times x minus, and our input was 2. And this would be the equation of our tangent line, just plugging into point slope form. Are there any questions so far? Okay, let's try this for a few different functions then. So here we have a function f of x equals 3, a constant function. So for a function like this, and my point of interest is x equals 0, for a function like this, if we apply our secant to tangent idea, we kind of have that idea, but this is also a straight line, so we think that we should know what the slope is, right? The slope of this ought to be 0. It would be pretty bad if our secant and tangent idea came up with a slope that didn't agree with our, you know, our basic algebra over here. So we probably want to at least look at a couple of examples like that. So here's my point of interest. X equals 0, y equals 3. I'll put a little star next to that one. And if I pick whatever point at x equals h, that's h units away from x equals 0, my x coordinate of the point of interest, and I draw the straight line through that, of course, my difference quotient is going to be 0, right? I have the same output, so my numerator, my rise, is 0. Now, importantly, my run is non-zero, because again, we take h to not be 0, just like above. So I have 0 over some number that's not 0, and that's just 0. This is true for any h, so whether I have h equals 1 or 0.1 or 0.001 or -1 or negative 0.1 or negative 0.001, the slopes of the secant lines are all just always 0. So the slope of my tangent line, I would probably guess, ought to be 0. As an exercise, kind of to do for homework, not to hand in or anything, but just for your own personal practice, consider a linear function. F of x equals mx plus b. Pick a certain slope and a certain intercept, whatever you like. Maybe it's 3x minus 1 or something. Pick one that you like. And for this linear function, well, we, on one hand, know what the slope ought to be. It probably ought to be 3, right? Go through the secant line, tangent line, difference quotient ideas and see if you can recover that same number, that same slope of 3. Again, hopefully that does work, right? It would be bad if we got some inconsistencies there. We're trying to generalize the idea of slope, not come up with a completely different idea of slope. So our new idea of slope should work for curvy functions where the previous one didn't work for curvy functions. But if I try to apply that to the simpler case of a straight line, it should still give me the same answer. That's something that I want to check whenever I do a generalization. And so as an exercise, pick a function and check that. Or if you want to, you can try to make the argument for the full just mx plus b in general and argue that the slope ought to be m. Okay, now let's look at a function like 1 over x. Now note that if I had my function f of x equals 1 over x that looks like this, and I ask maybe what's the slope at x equals 0, the pseudo slope, the slope of the tangent line at x equals 0, well, I mean, this is just fundamentally broken, right? At x equals 0, it's like I can't do 1 over 0. Everything's shooting off to an infinity. So there are questions where I don't have a suitable generalization to answer them, right? But if I ask it, say something like x equals 1/2, Well, this seems to be a pretty reasonable thing to ask, right? I could certainly draw a line that touches at that one point, and this seems like a pretty reasonable question to ask. So again, what are my 2 points? Well, I have my kind of point of interest, 1/2 comma 2, and I have my other point, 1/2 plus h comma 1 over 1/2 plus h. And again, h is not 0. My difference quotient, what does it look like? They have the rise, the difference in the y values, over the run, the difference in the x values. Note that because we're going h away from the initial starting point on the x axis, our denominator is always just going to be h. All right, so what do I want to do? I guess probably in the numerator, I want to get a common denominator. So I have a 1/2 plus h times h. And then this gives me 1 minus 2 times 1/2 plus h. Or this gives me 1 minus 2 over 2 is 1 minus 1. Gives me a minus h over 1/2 plus h times h. Or this gives me a minus 1 over 1/2 plus h. Or maybe I could make this look a little nicer by making it something like -2 over 1 plus 2h. That maybe looks a little bit nicer, just multiplying top and bottom by 2. And again, very importantly, h not 0. And again, I'm going to just kind of draw the table of values for h and d of h. And here I want to be a little bit careful, I suppose. I don't want to pick h to be like -1 because that kind of like jumps all the way over here, and I'm kind of going across the this point of singularity. I probably don't want to do that. Let me pick h to be like -0.1. That keeps us kind of nicely away from that trouble part. -0.01 and maybe -0.001. We'll see what we get on this side, and then we'll check the positive h's as well. So I want what? -2 over 1 plus 2a. And we'll start with a equals -0.1, which gives me an output of negative, whoops, that ended up behind there. That gives me an output of -2.5. So the slope of the secant line going through 0.4 comma 1 over 0.4 and 1/2 comma 2, the slope of that secant line is -2.5. If I go to -0.01, I get -2.04. And if I go to -0.001, I get -2.004. Kind of seems like this is going towards -2. Again, this is just a guess. We haven't proven this carefully, but it's at least an educated guess. And if I pick positive h's, say 1, gives me a slope of the secant line of -2/3. If I go to 0.1, that's what, -1 2/3. 0.01, getting pretty close to -2 now. 0.001, getting even closer. It seems like from the other side, we're going to -2 as well. And at this point, I probably feel pretty confident guessing that the slope of the tangent line is -2. And again, if I want the full equation of the tangent line, I just use point slope form with a slope of -2 and the point 1/2 comma 2. Are there any questions so far? Okay, so that is the tangent problem. We're going to look at the next problem, the next kind of canonical example, the velocity problem. And at first glance, these seem like two completely unrelated problems. The tangent problem is really a question about some geometric structure that kind of seems a little bit like a generalization of a slope, of a curve. And the velocity problem feels like a physics problem. So how are these two related? We'll actually see that we end up using very similar math for the two. So velocity problem, it's first important to note that average velocity is the change in position over the change in time. And often we define, say, average velocity on an interval, say A to B. So we can talk about the average speed over some time interval A to B. So the change in time would be B minus A. And then if I have some position function, let's say d of t, distance of time at time t, this is like d of b minus d of a, the position that I'm at the ending time minus the position at the beginning time. And we might already see the link, but if you don't, that's perfectly okay. So average velocity looks like change in position over change in time, or if I have a position function like this is my d of t function from A to B. Well, my average velocity, change in position over change in time, is just d of b minus d of a over b minus a, or that's just the formula for the slope of the line connecting a comma d of a to b comma d of b, right? That's just the slope of that line, that secant line, is really just our average velocity. So the slope of this secant line is the average velocity for the secant line related to the position function. So our black curve is our position at time t, and the change in position is what we call velocity, and our average velocity over a time interval is the slope of this secant line. Now we might want to ask, okay, I can figure out how to find average velocity now, but what about instantaneous velocity? What if I have a radar on a car and it says, at this point in time, the car was going 30 miles an hour. What do I mean by that? I didn't watch the car for an hour and see it move 30 miles of distance. So what do we mean by instantaneous velocity, that at this time the car is going this speed? Well, I guess kind of what I mean is something similar to above, right? I mean, if the time point of interest, let's say, is t equals a, then I take an interval from a to b and I let b get closer and closer to a. If I choose b kind of far to the right of a, then I get a secant line that's not close to that tangent line, or in other words, I get an average velocity that's probably not super close to my instantaneous velocity, right? If I watch a car that's, going on the highway a little bit and then goes on a side road and then stops at a red light and all of that, if I incorporate all of that information and I'm interested in how fast the car was driving on the highway, I've probably taken too big a chunk of time to sample from. If I start shrinking this interval, if I pick values for B that are closer and closer and closer to A, I'm kind of narrowing down, right? I might be looking at the car driving on the highway right now and the car driving on the highway 3 seconds later. It probably didn't change its position or its velocity all that much over that time interval. So that's probably going to be a much better approximation of its instantaneous velocity. And we can see the geometric link to the tangent problem. I'm taking secant lines that are getting closer and closer and closer. Whoops, that was a bad secant line. Closer and closer to the tangent line. And when I investigate slopes of those secant lines that I think are approaching the slope of the tangent line, that's really the same question as taking a big time chunk to estimate average velocity and then slowly chopping that down to a smaller and smaller and smaller chunk of time, a smaller and smaller and smaller b minus a difference to estimate average velocity over a shorter and shorter and shorter time period, and looking at that pattern and seeing if that approaches a number that we might want to call instantaneous velocity. So at the surface level look like two very different ideas, but I think one of the very powerful things in math that we discussed a little bit last time is this ability to generalize. We can say, okay, I have this underlying structure, this idea of the derivative that we're going to be working up towards. And these surface level problems, these two problems and some others might look very different on the surface, but it's really this underlying fundamental structure that's connecting them all. And if I understand that structure, then I can port all of that understanding to a velocity problem or a tangent problem or whatever other problem I want to understand. So a lot of times in math, we work directly on the structure. And you might say, when does this ever apply? Well, you can take all of those ideas and apply them to any of these surface level concepts or many others. Okay, so let's look at a practical example. Any questions so far? All right, suppose we have an actual function that represents the position of a particle at a point in time. It's d of t equals 2 sine of pi t plus 3 cos of pi t. And we want to find the instantaneous velocity at time t equals 1. So I want to find v of 1, v velocity at time 1, or the speed at time 1. Well, I'm going to compute average velocities over some interval. When we do a time average, a lot of times we just use the shorthand notation with these angle brackets. So this is the average velocity, and maybe with a subscript, say a to b. So if I do angle brackets with v of t inside, that means average velocity. And if I want to explicitly say what the time interval over which I'm taking that average is, then I use a subscript with that interval. So I'm going to be looking at the average velocity from, let's say, the time interval t equals 1 up to, let's say, b. And I'm going to choose different values for b. Now, of course, I'm going to not choose b equals 1, because if I did that, I can't really compute an average if I don't have any data to go off of, right? If I don't have a start and an end position, and a start and an end time that are different, if I chose b equals 1, I get, well, I'd get 0 in the numerator and 0 in the denominator, right? If I tried to plug in b equals 1, I get 0 over 0. That's an indeterminate form. It can kind of mean anything, or it can blow up, or it can do all sorts of things. So I don't want to plug in b equals 1 and get 0 over 0. but I'll plug in other values of B that are close to 1. And what is this? This is V at B minus V at 1, or wrong letter, D at B minus D at 1 over B minus 1. And I want to choose values of B that are not 1, but that are close to 1. So let's cross our fingers and all right, so fingers crossed that this works out. Oh, and I guess I probably let me actually go back and call this B so that it doesn't get confusing. All right, so we have 2 sine of pi B plus 3 cos of pi B. And what do I get when I plug in B equals 1? I get -3. So D of 1 is -3. Now to find my average, I'm just going to plug that in, D of B minus a -3 or +3 over B minus 1. This is the function I'm interested in for values of B near 1 but not equal to 1. So now let me plug this in. I think I can just do all of this plus 3 divided by, let me actually expand this for just a minute. I need B minus 1 on the bottom. Okay, B minus 1. All right, so I have D of B looks good, minus a -3 minus D of 1, so +3 over B minus 1. Looks good. And you can see actually, I kind of had left B equals 1 in there. If I try to plug B equals 1 in, it comes up as undefined. It's 0 over 0. We're not sure what to do with that. But again, what is my goal? My goal is to start away from 1, say, looking at an average velocity over the interval 1 to 2, and then work my way towards a smaller and smaller and smaller interval of time. So if B is, for instance, 2, then my average velocity is 6. But again, this is a pretty big chunk of time from 1 to 2. We can probably do a little better than that. Keep in mind, in this case, I'm looking at the average velocity from time 1 to time B, so I want to pick B's that are close to 1. In the last problem, we were looking at our input being a deviation from our starting point. So we wanted that deviation to get close to 0. Here we're looking at the actual, x coordinate, so to speak, of the second point. So we want that x coordinate of the second point to get close to the x coordinate of the first point to 1. That's why we're plugging in B's that are closer to 1 and not H's that are close to 0 like we had been before. So when B is 1.1, we get -4.7. When B is 1.01, we get -6.13. If I plug in a couple more zeros, I get -6.28. What do I have? 4 zeros. And we actually might guess that maybe this is like negative 2 pi or something like that, but it's certainly something like negative 6.3. And then likewise, if I were to go the other direction, instead of instead of taking time intervals that are after the time point of interest, one, I could take time intervals before. I could go b equals 0. Again, keep in mind that the restricted value is b equals 1. We can't plug in b equals 1. We're looking to take values of b that are closer and closer to 1. So if we start at 0 and work our way up, that's perfectly fine in this case, but we wouldn't want to plug in h equals 0 in the previous examples. But b equals 0 gives me an average velocity of negative 6 on that interval from 0 to 1. If we jump up to say 0.9, that's getting a little closer to 1. That gives me negative 7.6 or so. 0.99 gives me negative 6.43. And if I put on a couple more nines, I see I get about negative 6.28. That 4, 5, I think. So again, I see the same negative 6.28. I'm pretty confident that my instantaneous velocity is somewhere in the ballpark of negative 6.3-ish. Maybe I might even go as far as to guess that it would be negative 2 pi. Now, what does an instantaneous velocity being negative mean? That's kind of an interesting question, right? Speed is always positive. But what we're kind of talking about here is suppose that we have a position axis d where a particle can be. It can be further to the left or further to the right. It's only one dimension. And here is 0. And as time progresses, my particle might do whatever it's doing. Sometimes it's going to be moving in the positive direction. When it's moving in the positive direction, it has a positive velocity. But sometimes it's moving in the negative direction. That's when it has a negative velocity. So the particle's speed at time 1 seems to be, its speed seems to be about 6.28. And the negative indicates that it's moving in this direction. So maybe we're like, maybe this is time 1. And whoops, here. And we're kind of moving in this direction. Any questions on this? So we can see even though the surface level looks very different between the tangent problem and the velocity problem, the underlying mathematics, the underlying structure, and the approach to figuring out what I think the answer is really the same between the two. I also note that even though these two problems are effectively the same, I can set either of them up in either of these two ways. I can either talk about the x coordinate of the first one versus the x coordinate of the second point, or I could talk about the deviation from the point of interest, h. Right. I could have set up the tangent problem as 2 comma 8 and b comma b cubed and let b approach 2. I could have done the tangent problem that way. I would have gotten very similar answers. I would have gotten the same end answers. I'd have gotten very similar work. Or I could have set the velocity problem up as a deviation from the point of interest, going from a to a plus h, that time interval, and let h get closer to 0. Again, I would have gotten the same end result, slightly different, but very similar work for the intermediate work. Two different approaches to do the same thing. Okay, so let's take a look at this next example then. So suppose in this case that we have some distance information from a bike race or maybe a running race or whatever you want to imagine it is. And we have some distance information for this person at different times. So let's say the time in seconds is listed here, 0, 1, 2, 3, 4, 5, and the distance from the start line is listed here for each of those times. So 0, 1.4, 5.1, and so on, meters from the starting line. And maybe I'm interested in knowing what's this person's instantaneous velocity at time 3 seconds into the race. I have distance information, but not velocity information. And I also don't have a function where I can plug in numbers arbitrarily close to 3 and get outputs and make an estimate that way. I have to use the data that I'm given. So what do I have? Well, I have a function that's distance as a function of time, goes through 0, 0, and it has some other points. I'm just going to kind of draw a schematic of the points. These aren't meant to be super accurate. And I could imagine that there's a function giving rise to these points. But I just have a sampling of this function. The only data, the only inputs I can plug in and the only outputs I can gather are from these black points. 0, this is 1, 2, and 3. So this is my point of interest here. Oh, and I guess I left one off. 4 and 5. So what might my approach be here? What would be my best way to construct a guess at what I think the instantaneous velocity is? Well, here I can really leverage the connection between these two problems. I know that this problem is fundamentally the same as the tangent problem. In other words, really what I'm asking here is equivalent to the geometric question for my tangent line at t equals 3. What's the slope of that tangent line? The line that's tangent to this kind of imagined curve, the blue curve, that we don't have the data for, but we kind of imagine existing in the background here. Now, I mean, I suppose I could just look at the average velocity from 3 to 4. I mean, I could do that, but I noticed that that secant line is actually quite a bit steeper than the tangent line. I guess I could also go the other direction. I could look at the average velocity from 2 to 3, but I noticed that that secant line has quite a bit shallower slope than the tangent line. So this is too steep, and this is too shallow. In fact, I can actually get a much better approximation, and this is often true in practice, and there's actually a decent bit of math supporting this, and we'll actually we might see that as an example at some point in the course. I've kind of run out of, oh, I can use red, okay. I can actually go in both directions. I can actually choose to go from 2 to 4. And at first glance, this seems like it ought to be a worse approximation because I've taken a bigger chunk of time. Shouldn't I be choosing the smallest chunk of time I can get away with? Well, on one hand, that's nice, but on the other hand, for something like like an increasing and concave up function like this, when somebody's just starting out a race and getting moving, that's going to lead to biases, strong biases in one direction or the other. If I take the later time, they're going to always be running faster than the time I'm interested in. And if I take the earlier time, they're always running slower than the time I'm interested in. But by going both directions, like sometimes they're running faster and sometimes they're running slower, that gives me a bit of a sampling from both sides of the point of interest. So there are occasions where if I'm stuck with taking a fairly big chunk of time, I might want to go even bigger so I can get a more representative sample. And I can actually see that the slope of this secant line is going to be much closer to the slope of the tangent line than either the right or the left, um, single unit deviations. So if I wanted to estimate this instantaneous velocity, I would actually use from 2 to 4. I don't really want to go from 1 to 5 because then I'm needlessly taking a bigger chunk of time, right? I can already go a little bit to the left and a little bit to the right. I don't want to go a lot to the left and a lot to the right. So what's my average velocity on 2 to 4? I'm going to say that that's approximately my actual velocity at 3. Now, it's not like in some sense demonstrably wrong to use the interval 2 to 3 or 3 to 4, but we're just saying that practically speaking, what is most likely to give you the best approximation? Probably the interval 2 to 4. And we can really see that clearly through the link to the tangent problem. We can see that that secant line is going to line up with the slope of the tangent line much better than going 2 to 3 or 3 to 4. And the average velocity on 2 to 4 is, well, that's d at 4 minus d at 2 over 4 minus 2, or that is 17.7 minus 5.1 over 2. So that's 12.6 over 2 is 6.3, and this would be in meters per second. Why is it in meters per second? Well, my distances are in meters, my times are in seconds. So I can always, one nice thing about application problems like this is I can check my units. Is meters per second a speed, a velocity? Yeah, that's the unit that I would expect. So that's good. Are there any questions on anything? Oh, I see there's a question in chat. If the velocity value indicates a direction, does that make it a vector since it has a magnitude and direction is? In a sense, yes. We would still call it a scalar because it's only one number, but because we allow for numbers to be positive or negative, but there's definitely a sense in which it's a velocity. So, or in which it's a vector. So velocity is always a vector quantity and speed is always a scalar quantity. So we would say that speed is like the absolute value of velocity in one dimension. So yeah, there's a sense in which it lines up with that idea. But I wouldn't take that too far at this point. Yeah. Any other questions? Okay, so let's look at another example. Then we're back to a situation where we have a full function to work with. This is going to be our typical situation. This is kind of a one-off, this might be common in real life, but for this class where we're looking to understand the structure of how these things work, we're usually just going to work with the function because it's easier to work with. Suppose we have the position of a particle described by f of x equals the cube root of x. Find the instantaneous velocity at time 0. So what's v of, oh, let's not do it in red if we don't have to. What's v of 0? Well, I think of that looking like, it looks like the average velocity from 0 to, and let's do this one with a deviation just to show the other way of doing it. Maybe for small h. So we're looking to approximate our instantaneous velocity by taking an average velocity from the time point of interest to a time point that's a small deviation, a small time h away from that initial point of interest. Importantly, this is a small deviation and not zero. Again, if we plugged in h equals 0, we have problems with either the geometry up here, how do we get a line when we don't have a second point, or with kind of, well, what does an average velocity over just one point in time mean? It doesn't really make a whole lot of sense. But what is this? This is f of 0 plus h minus f of 0 over 0 plus h minus 0. Or I guess this is just, I know that f of 0, the cube root of 0 is just 0. That's f of h over h. So what happens to this function as h goes to 0? We'll maybe say start at 1, and then 0.1 and 0.01 and so on. So let me plug this in over here. We are looking to do, oops, cube root of h over h. Or let's call it, well, we'll do h to the 1/3, oops, 1/3 over h. Does that look good? That looks good. And we'll start with, say, h equals 1, and we get an output of 1. If I do h equals 0.1, I get an output of 4.6 or so. If I do 0.01, I get 21.5. If I do 0.001, I get 100. This is kind of looking unfortunate, right? These numbers keep getting bigger and bigger. If I go another power of 10, I get 460. Another, I get 2,000. Another, I get 10,000. It kind of seems like these are getting larger and larger, like heading off to infinity. What if I were to approach h from the negative side, say -1, h equals 0 from the negative side? -1 gives me an output of 1. -0.1 gives me positive 4.6. It actually looks pretty similar, right? It's actually going to be exactly the same. So whether we're plus or minus doesn't really matter. Well, what's going on here? Well, if we look at the geometry, we know that, well, I know that x cubed looks like this. So the cube root of x, this is y equals x cubed. That means x equals y cubed. In other words, if I swap the roles of x and y, or sorry, y equals x cubed. If I swap the roles of x and y, I get x equals y cubed, or y equals x to the 1/3 power. And that's geometrically equivalent to flipping about the line y equals x. In other words, the cube root of x looks something like this. And we actually have this kind of like vertical tangent here. So we actually have a line with kind of like infinite slope. So unfortunately, the answer to this at this point is kind of just question mark. We kind of, for an instant, have instantaneous velocity. That's kind of an unfortunate answer, right? This is one of those situations where we end up with a result that's kind of somehow indeterminate, somehow doesn't seem like it's well defined. This is one of those edge cases that we're going to have to build up a little bit more mathematical understanding to really handle confidently. So sometimes we get a very nice intuitive answer like some of these previous ones. And sometimes we say, well, I'm not really sure how to handle this. Maybe we need to dig a little bit deeper. Maybe we need to build up a little more of the mathematical foundation before we can attack a problem like this. It kind of seems like it's going to infinity, but can we like really say that? Are we comfortable saying that? We probably want to investigate a little further first. And then a last example here, we have a particle whose position is described by g of t equals absolute value of t. It's not a bad function. You pick a value of t, you can get an output for any value of t. And we want to find the instantaneous velocity at time 0. So again, if I look at my uh, average velocity on, I'm interested in v at 0, and that's approximately the average velocity from, say, 0 to, let's say, 0 plus h. Well, this is going to be my position at 0 plus h minus my position at 0 over 0 plus h minus 0. Or that's going to be g at 0 plus h, or, well, I could just write g of h, I suppose, minus g of 0, but the absolute value of 0 is just 0, so that's just minus 0, and then over h. So I end up with g of h over h again, kind of a similar structure to what I ended up with up here. And I might be really tempted to say that this is just, oh, that's just h over h is 1. We need to be careful though, right? Because h not equal 0, we're typically thinking of it being small, something near 0, but it could be positive or negative. Well, if h is positive, then g of h over h, well, that's just absolute value of h over h, but h is positive, so absolute value of h is just h. Then we can do this. But there's nothing saying h can't be negative. H could be negative as well. If h is less than 0, absolute h over h is negative h over h, or negative 1. Or another way of looking at it is geometrically. As I'm kind of coming in from the left-hand side towards this 0, 0 point, if I pick any sampling point over here on the left to go along with my point of interest at 0, 0, we're going to very confidently assert that the slope is negative 1. It's going to be exactly negative 1 as we pick h to be negative 2, negative 1, negative 0.1, negative 0.01. It's always exactly negative 1. We'll very confidently assert the slope is negative 1, but as we approach from the right, any second point we pick that's to the right of 0 is going to give me a slope of plus 1. What should the slope of my tangent line be? One side says negative 1, one side says plus 1. They can't agree. Well, what's the issue here? What's the fundamental issue? Well, let's try to do what I did all the way back at the beginning. Let's try to take the point of interest and zoom in on it. The world is locally linear, right? Well, I mean, I suppose it usually is. Because if I take this and zoom in on it, it looks exactly the same. If I zoom in more, it looks exactly the same. It's just as pointy no matter how much I zoom in. It's just as nonlinear no matter how much I zoom in at this point, 0, 0. Right. what should a tangent line to it look like? A line that touches at only one point. Well, I mean, if you imagine taking a two by four and you have a nice, curvy, whatever, tire or something you're laying it on, if you put a dot on the top of that tire, you have to pick just the right slope for that two by four to get it to lay on that dot. But if you have like a knife edge, you can wiggle that two by four a whole lot and still get it to just contact the edge at one point. I could take a function like this, a straight line like this, or like this, or like this. I have lots and lots of lines that could touch this function at that one point. So unfortunately, in a situation like this, it seems like I don't have a unique tangent line. The geometry kind of fails. This geometric idea of zooming in and looking more like a straight line fails here. And I saw that fail directly in the algebra as well. When I tried to use that algebraic structure that I built up, I got a disagreement. Sometimes it feels like the tangent line maybe ought to be one. Sometimes it feels like it ought to be, or sorry, the slope of the tangent line. Sometimes it feels like that slope ought to be -1. We get a disagreement. So in a situation like this, we would say that this result doesn't exist. We don't have an instantaneous velocity here. Or kind of another way to think about it, right, is if we try to put this into real world, say physics, if you're going in this direction and then you instantaneously change and go another direction, a completely different direction, you would have to like apply infinite force over that little infinitesimal time period to change your direction like that. And you can't apply infinite force, right? The best we could do in a real scenario is apply some force for a little bit of time and get a kind of nice gradual transition from one to the other. But to change at a point like that, we would have to apply like an infinite force, and we can't do that in the real world. So, and stats today are one of our quotes of the day. The quote that goes with the material that we're covering was from a statistician that all models are wrong, some models are useful. Maybe the absolute value equation models something very nicely most of the time, but we want to be aware that, if we're really interested in this point at 0, 0, if we're really interested in modeling that point, maybe this is not a great physical model if we're trying to model something in the physical world that way, and we're really concerned about that point 0, 0. Okay, any questions on anything so far? All right, so that's the kind of introduction to this chapter 2, where we're again kind of going to dive into, for the next couple of sections, some of the underlying structures, like really building up the mathematics of these ideas of limits, which is going to bring some formalism to the kind of things that we were doing over here, just kind of plugging in lots of numbers and seeing what happens. We're going to bring some nice formalism to that. We're going to have some properties that we can work with as a result of that. And really the goal of chapter 2 is to reach 2.7 and 2.8, where we introduce the idea of the derivative, kind of the first really major idea in the study of calculus. I mean, limits are extremely important, so don't get me wrong, but they kind of are important because of their relationship to derivatives and some other things in calculus. So we're going to be covering a bit of material that you might say, why are we going through all of this right now? Well, the goal is when we have a nice situation like this, things work pretty nicely. But how do we understand, how do we make heads or tails of situations like this one that don't work so nicely, or like this one that don't work so nicely, and do it in a very careful manner. Okay, any last questions before we break for today? All right, so remember the intro, the chapter 1 Review homework is due this weekend on WebAssign. Make sure to knock that out. Again, that shouldn't take you super long time. It's mostly review stuff, and it's really the goal is to review some of the material and also to get logged into WebAssign, get used to using the system and how it works and everything before the homework on the new material. And we'll continue with chapter 2 next week. So have a good weekend.